Thank you for the nice introduction. Great. Good afternoon, everyone. My name is Kevin Zhang. I'm a fifth-year PhD student in Computer Science of Federated University. And today I'm going to present our work, CENSOR, Defense Against Gradient Inversion via Orthogonal Subspace Bayesian Sampling. So this is a joint work from Purdue and IBM. And first, I want to give you guys a quick recap of federated learning. So FL is a distributed learning paradigm that can enable different parties to train the model together to get a high quality and strong privacy protection. And it has many different applications like network prediction, credit prediction, and IoT device aggregation, etc. However, when you use FL, is your data really private? And you may think, like, as a client, my data is kept locally and I never send it to server. It should be private. But the researchers find that with an honest but curious server, or like some malicious guy that can eavesdrop the communication channel, actually they can reconstruct the private input from the gradients, even without like touching your local data. So how does the gradient inversion works? So basically, gradient inversion is a technique that can like reconstruct the gradients only reconstruct the gradient from the that to communicate with the server and without touching your raw data. So usually they initialize with dummy inputs and they like do the gradient matching with stochastic optimization, or they use some generative model to perform the gradient that can reconstruct the output set from the input. So this basically demonstrates a privacy leakage concern in federated learning. Like even without touching the raw data, it can still like invert some meaningful images from the only from the gradient. So here comes to our threat model. So basically we assume an honest but curious server. So basically the adversary can know the model architecture and the local gradient shared by the clients, and the adversary can access the public available data sets, and it can utilize anything like the pre-trained model like GANs or any generative model they can have. So we have a relatively loose assumption on the adversary. So with that, I introduce some representative gradient inversion attacks. So basically, there are differences mainly on the initialization or the distance function, or whether you use the generative model. So basically, the first two works, IG and GI, are stochastic-based methods, and the last three, GGL, GIS, and the GFD, are based on the generative models. So the first work, like IG, they optimize on signed gradients with cosine celerity, and they refine the inputs initialized from Gaussian noise. And GI initialize the inputs with the Gaussian noise, and they apply the Adam optimizer with regularization. And for GGL, they leverage the GANs with the Kel-based regularization, and they optimize with Bayesian or some covariation metrics. And for GIS, they employ the negative cosine similarity as the like a gradient dissimilarity function. And for the gradient inversion over the feature domains, this is the most state-of-the-art work. And they utilize the intermediate GAN features and optimize with a warm-up strategy. And they also have many different defense methods. So basically, the first is the noisy gradient. Like they basically add some like the Gaussian noise to the gradient, and they can reduce the privacy leakage, but can significantly like degrade the utility. And for gradient clipping, they basically just bounce the gradient magnitude by clipping the values, but fails to prevent the privacy leakage. And for for the gradient specification, they just zero out the smaller values, and they only keep the large values and transmitting these large values. But our experiments shows that this method still leaks the information. And for the Soteria, it basically is the most state-of-the-art of the defense, and it balances the utility and the privacy through the optimization. and the gradient masking, but this method is kind of very computationally expensive. And we have two interesting observations to motivate our work. And the first observation is basically telling existing attacks, they only succeed in the early stage of training. So how to interpret this figure? So in the left-hand side is original input, and in the right-hand side is inverted image in different training runs. Like each row is the attack I introduced in the previous slides, and each column represents different FL rounds. And you can see like GIFD has the most effective in the first, zero training rounds. And we can see overall the gradient inversion is the most effective in the early training stage, and with especially with batch size is 1. And you may also wonder, it seems like GGL also works, but is it really like that? So here comes to our second observation. Actually, GGL generates high quality, but it is typically low fidelity images. And we observe that, from the figure, the first row is the original images. Like you can see, the bird is in different positions, and it may sit in the grass or on the stone. But you can see GGL, when GGL try to reconstruct the input, it's always reconstruct the bird, but in a different angle. So basically, that's their methods insights, since they leverage the label information. So from this, we can say even with the GGL fails to reconstruct the exact input, but it still leads to the privacy leakage. So we see two observations we motivates our work, CENSOR. So before diving into details, I will give you guys a high-level intuition. CENSOR basically just sample the gradients in a subspace that is orthogonal to the original gradient. You can see the original gradient sits in the blue parts, it's a GL, and actually in a neural network it is over-parameterized model, and there could have millions of different orthogonal spaces you can sample. And here we demonstrate it have G star, G1, G2, blah, blah, and we select the one with the lowest loss. And here is our, sorry. Cool. Thank you. Here is our method, CENSOR is layer-wise orthogonal subspace perturbation. Basically, with the input original image, and it propagates to the different layers of the model, and in each layer we are doing the orthogonal subspace projection. We select the one with the lowest loss, and finally we after the layer-wise operation, we agreed to a protected gradient capital G star, and we return this protected gradient to the server. And with that, the privacy is protected. And comparing to all of the existing defenses like DP or gradient clipping, gradient specification, our method demonstrated the most effectiveness. And here we have the quantitative and qualitative experiment. So basically, we see various defenses and attacks on 3 data sets, like ImageNet, FHQ, and 710. Here I take the ImageNet as an example. So here we can see in each row, it means different defenses, and the last row is our method. And in each column, it is different state-of-the-art attacks, and in each sub-column is the metrics. And for MSE and the LPIPS, is higher the better, demonstrate our defense. And with the PSNR and SIM, it is the lower the better. And we can see CENSOR outperforms existing defenses in almost all cases, and it significantly can surpass the state-of-the-art defense, Soteria, with up to 114%. And here comes to our qualitative experiment. and we choose 2 examples from InverNet and FFHQ. So in InverNet, you can see in the left-hand side is original input, and in the right-hand side is different tags, in the different tags in the column, and for each row is different defenses. And the last row is ours method. We can see CENSOR effectively can prevent the attacks from inverting any meaningful images. And we also perform the convergence study. We select 100% clients performed in several 10 data set, and the data distribution is non-ID. And for each round, we randomly select 10 of them, and we perform the FL for 2,000 rounds. And here in the figure, each trial basically means how many different trials we are trying to sample from the orthogonal subspace. And we can see with different trials and comparing with original FL training, both original and the CENSOR in different trials can converge to a similar level, and the observation also holds in the test. And here comes to our adaptive attack, EOT. So we basically evaluate EOT to perform. Basically, EOT is to perform the gradient transformation multiple times to take the average gradient over the several rounds to approximate the gradient. So basically, it means they know how we defend. And even with this kind of adaptive attack, we can see in both ImageNet and the FFHQ, both our methods can still hold effectiveness under the adaptive attack. So that comes to conclude our work. So basically, CENSOR is designed to mitigate the gradient inversion attacks, and the CENSOR can sample the gradients within a subspace that is orthogonal to the original gradients, and the CENSOR can enhance the data privacy and maintain the model utility. And our paper code and slides are available in the website. Thank you for your time, and I'm open to the questions. And by the way, I'm on the job market for the next cycle.
Okay, let's thank the speaker.
Thank you.
Any questions?
Here?
Sure.
Thank you for your presentation. I have a question about how would you compare your defense against those secure aggregation protocols?
Which part do you specifically mean, how to compare?
So what is your advantage against those secure aggregation protocols?
Oh, that's a great question. Basically, that's why we have the Bayesian sampling and the orthogonal space in the in our title. Actually, the intuition is when the model is over-parameterized, it can have millions of different choices in the high-dimensional space. And if you can, project the gradient into a space that is orthogonal to the original gradient, it's very hard for the attacker to find the specific data space, try to invert. So basically, the orthogonal space, it can maintain the utility, and in the same time can prevent the attacker to find that original one. Yeah.
Okay, thank you.
Thanks.
Next one. Could you please introduce yourself?
Hi, my name is Claire Van Zwieten. I am the alumni specialist at the Internet Society. Great presentation. I'm very curious, what would you say is the human impact of this work? So how would this project maybe affect your neighbor?
Oh, first I want to thank the Internet Society. I'm one of the fellows that's selected by the Internet Society. And very interesting, I think one of the perspectives could be, since our focus is on federated learning, so basically federated learning that can be applied in, one of the real world cases, Google are using next word prediction for the keyword. So do you really want others to know, what do you type for for every day, and your password or your user private interaction with many different different websites. So if you want to protect that, so use our method.
Thank you.
Thanks.
Okay, any other question? If not, I have also a question. So have you also considered attacks that are targeting the aggregated model? So which ones?
You mean like the federated learning protocol, like how they
No,
use it?
the aggregated model on the aggregated side. So you,
So basically, we are a defense, and the threat model is the attacker is assuming the server, like they actually are the
server
honest
is not
but
trusted,
curious.
yes,
Yeah.
honest but curious. But what kind of attacks? That inference attack, membership attacks, or is it all general attacks?
It's a general data reconstruction attack. I think
Okay.
it's pretty similar with membership inference, but membership inference or property inference, they are suspect to a special property. But data reconstruction is try to know what is original training data looks like.
Yes, but inference attack is about information leakage, but the other one is that reconstruction of the whole data. So it's a different adversary model.
Yeah, exactly.
Okay.
Yeah, exactly.
Okay. Thank you very much for your talk.